Let's Boltzmann Q&A. What data structures are used in the lattice Boltzmann method? So when we discuss the data structures for the lattice Boltzmann method, the first thing, of course, we have to do is to look at the lattice that we are using. The lattice is indicated by the nomenclature DDQQ, where this D is the number of dimensions and the Q is the number of lattice speeds or populations. And of course, for each node, you need to have one population. So you would have Q nodes per population. And then on top of this, you usually would have for every dimension one velocity component and one pressure component. This, by the way, does not need to be stored because it is required only during the collision process, but usually you need this information for post-processing, and therefore you will usually allocate memory for this too. Okay, now how can this data be organized? There are, of course, several options, and the two most important are the array of structure and the structure of array option. So in the array of structure option, each node is stored as a vector with all its components with all its Q populations. And the other version, the structure of array, stores all the distributions or all the populations going in a certain direction in a list of including all the different nodes. So here you have now Q arrays with, say, n nodes. If you have with n components, if you have n number of nodes, and in the other case, you will have n nodes with all its distributions assigned to it. Okay, now there's also different ways of addressing your information, and the two important here are, of course, the direct addressing and indirect addressing. So direct addressing means you store all your nodes, or this can also be done by storing populations, by associating each node with its coordinates in a rectangular matrix. So you can actually address everything by their coordinates. And you do not need to store any neighbor information. This is a good thing when you have a regular domain that fits good in a rectangular. So sometimes you have more complex domains, in particular when you use grid refinement. So when you have different resolutions in the system, then usually it is more efficient to store your data in an unstructured fashion, and this then requires indirect addressing. This means every node has to be indexed with a number like this here, and then for finding its neighbors, usually we need some links to each node needs some links for finding the neighboring nodes. So why do we need to know the neighboring nodes? This has, of course, to do with the streaming in the lattice Boltzmann method. So we need to move the distribution or the populations from node to node. And this can also be done in different ways. So the first way to do this is the pull scheme. What the pull scheme does is it takes information from neighboring nodes and pulls them from there and puts them back to the position of interest, which is then this one. And the push scheme takes the information from a node and transfers this to all the neighboring nodes that are connected with it. Okay, so now these are the two options for the streaming, for organizing your streaming, but there is more to say about this. Namely, you can also do this in different ways, more or less efficiently. So what we have to remember when we move our data is that because we cannot process all the nodes simultaneously, so each node in parallel, if we could do this, we could simply read from one matrix and write back to the same matrix, because on the computer we always have some form of sequential processing, so we would process our nodes in sequentially. We need to read from one matrix, call it B, and write it to other matrix A. Because this is necessary, because we write from a different position to which we read from a different position than we are writing to. And in this case, it is very important so that we do not overwrite information that is still in need during the same time step. So the same problem appears for the push and the pull scheme, even though we have now written it here in the pull version. So what you can do to deal with this is for example the following. So the simplest way of doing this would be taking splitting between the streaming and the collision. So you do the streaming from the matrix B to the matrix A, and then in the next step you use the matrix A as a pre-collision state. You apply the collision operator and write this back to the matrix B, and after this collision you return back to the first step. So this actually is stupid, because what you're doing here is you have two distributions, so matrix A and B, and you need to read all the data twice, once when you are streaming and when you are colliding, and you have to read it twice, and you have to write it twice. So this can be improved by the merging of streaming and collision. And this is then done in the following way. So you read from the matrix B again, then you apply the collision operator directly, and you write this to the matrix A. And then you have to read each data only once and write it only once. And then what you need to do in the next time step, you have to reverse the order. So you first read from matrix A and you write to matrix B. And then you return back to where you started from. And by exchanging the order of matrix A and matrix B, you do not need to read data twice per time step, so you read everything only once. So this is much faster than the first version. However, it still has some disadvantages, because it needs two representations of the distribution function. So everything has to be stored twice. And there are nowadays algorithms, of course, that can deal with this merging of streaming and collision, and at the same time use only one matrix. And there are many of these algorithms. Some of them only have with different qualities and properties probably. So here I only briefly address two of them, and I will always only be very brief. So if you don't get all of this, you probably have to go back to the original publications on this. So the two we are looking at is the periodic shift and the Esotwist. Periodic shift is a very old algorithm. I believe it's almost as old as the Lattice-Boltzmann method itself, and it has different names. It comes by different names. This is probably one of the original names is Lagrangian streaming. So what it does is relatively simple. We start reading data from a particular node. So we have a structure of array arrangement, and here we are in a certain location where we read our data. We do the collision and we write the data exactly back where we read it from. So because we write it back where we read it from, we don't have any problems with the collision of different nodes. So we are, as we said, thread safe. We cannot overwrite anything from our neighbors, and therefore we need only one matrix. However, we have not streamed our distributions now, and the way we stream our distributions is simply by reinterpreting the position of the data in these arrays by going in the next time step, t equals to 1, we go one step in the opposite direction to where the particles were streaming from, and read in the next time step for the same node the data from these locations, and do the same thing again. And so this proceeds on. So the data is moving further and further away, and once it goes out of the range of the array, it simply enters the array from the other side. This is why it's called periodic shift. Okay, so this was one of the first or probably the first in-place streaming algorithm, and another one that we are using is the esoteric twist. Esoteric twist keeps this data locality. So in the periodic shift, what happens is that the data goes further and further away. In esoteric twist, we keep the data locality, and what we do here is a combination of both pull and push, but we also we write the data to the position where we originally read it from. So, and here we distinguish between the pre-collision state and the post-collision state. So what we do in pre-collision is we read the data like indicated here, and then for the post-collision state, we write the data back in the same locations as we were reading them from, but we switch the directions of the particles. So by switching the direction of the particles or the populations, these populations have actually moved one step, yeah, implicitly. Then we use this inverted interpretation of the arrays in the next time step to read them again, yeah, and do this again and again. And what we see here, we are always switching the interpretation of this array from time step to time step. However, we still have this data locality, so we only address a particular neighbor, and the interesting part is that we always only address a neighbor in a particular direction. So this is also the reason why we are using Esotwist. As I have said before, this periodic shift is one of the oldest algorithms, so it has been around for a long time, and Esotwist is relatively recent. So why, if we have periodic shift, would we bother to introduce Esotwist? So the reason why we don't want to use periodic shift is because periodic shift doesn't work very well with indirect addressing. Actually, if you use direct addressing, periodic shift is a very good idea, but with indirect addressing, it's not so easy, because if you use indirect addressing, you have to remember that the data locality is not guaranteed in periodic shift. So in order to know your neighbors, you need to have pointers to basically in basically all the different directions. So now if you sit down a little bit and think a little bit harder, you can reduce this amount of information that you need somewhat, because you know that the particle or the distribution at the resting velocity, this is actually not moving at all. So this does not need to have a link. Yeah, so this can be stored without any link. And because arrays or distributions that go in opposite direction, they would have parallel arrays. We need actually only links to one of them, so we can actually subtract from Q, we can subtract 1, and we can divide this by 2, and then for example, in the popular D3Q19 lattice, we can reduce the amount of pointers that we need in indirect addressing for periodic shifts. We can reduce this to 9 pointers, which is of course quite good, but still 9 pointers are 9 pointers. So in esoteric twist, because you keep this data locality and because you need the neighbor only in one direction, what you can actually do is you don't need the pointers to all the lattice directions, but you only need the pointers to the directions in the cardinal directions, namely in X, Y, and probably Z direction. Yeah, and then because you have this data locality, what you can still do is you can use pointer chasing. So if you need to go, for example, to this node here, so node here, you need the information only in a specific direction. Yeah, but you also need it from this node here. So you would actually, in 2 dimension, you would require information from 4 different nodes, but you don't need this information, so you don't need the link to this node here, because if each node has a link in Y direction, what you can do is you can follow the X direction and then go to the Y direction, and then you end up here. So this is pointer chasing, and this means what you require now is only D neighbors, which means for the same lattice that in periodic shift would need 9 pointers, we now only need 3 pointers, which is of course significant reduction in memory requirement. So talking about these algorithms in more detail is of course something that requires more time. Probably we'll do this in the future, in particular if questions arise and you write them in the messenger. Okay, thank you very much.